For objective 2, you will be able to use volume to find geometric probability. So remember, probability here is just a measurement of how likely an event is to happen, and we're using geometric probability when you have an infinite number of things that you're trying to count up. Compare this with, let's say, the probability of rolling the number 1 on a 6-sided die. Well, that's really easy to count because there's only one number 1 out of 6 possible sides on a die. But whenever we're, let's say, throwing a ball on this skee ball little game, the ball can land anywhere within some sort of region, and whenever you go to measure that, you can't just count up the number of possibilities. Instead, I have to use geometry in order to calculate an infinite number of outcomes. If it's one dimension, then I use lengths. If it's two-dimensional, I'll use areas, and as you can see in this particular example, we're going to be using some volumes. Okay, so let's let solid A, or let A be a solid that contains solid B. Oh, where the heck is solid B? Oh, here it is. Okay, if a point K in A is chosen at random, then the probability that the point is in solid B is just simply the ratio of volume B to volume A. Right here is our little formula. Probability that K is in B is the volume of B, that's what we want, over the volume of A. Everything that's possible. Remember that it is favorable outcomes over total outcomes. So let's take a look at our first example involving volume geometric probability. Man, that was tough to say. Exercise 6. An inflated ball with a diameter of 1 meter is put into a cubed shaped box so that the edges of the ball are tangent to the face of the box. That word tangent right there just means that it touches at a single point. So it'll touch over here at the center, here on all of its faces, and so on. Okay, what is the probability that a randomly chosen point in the box is not in the ball? What does this mean? It means that whenever we randomly select some sort of point inside of this box, it's not inside the ball. So it's in all of this. It's in one of these little white empty spaces right there. And again, there's an infinite number of places where that point could possibly be chosen. So in order to cover all of them, we're just going to find the volume of these pieces. Okay, let's come over here so I have more space to write. So let's strategize here first. We want a probability that the point is not in the ball. So maybe I write something like this. K is not in the ball. All right, and again, we're going to use some sort of volume. So my favorable is my point being chosen any place outside of that ball, but inside of the box. How do I get that volume? I just subtract the two volumes. I subtract volume of box minus the volume of the ball. And then my total outcome, of course, is everywhere you can possibly choose a point, which is the volume of the box. Okay, so we've got a strategy here on how to find the probability. Now let's find, each one of these numbers here, the volume. Given that the diameter of the ball is 1 meter, so from here to here, that diameter is 1. Maybe I just draw that in here. My diameter, boop, is 1 meter. Well, that of course means that the box here is 1 meter by 1 meter and 1 meter because the ball fits snugly right into that box so that it's tangent to each of the faces, touches at a single point, right? It would touch right there, it would touch right there, and then so on. Okay. This also means that the radius of this sphere is a half. 1/2 of a meter. All right, now we have enough information to find our volumes. Let's first find the volume of the box. Well, it is a cubed. We find the volume of a cube by side cubed. 1 cubed, which is pretty much just 1 meter cubed. Oh, that was tough. Okay, And let's find the volume of the ball here. Okay, it is a sphere, so we're going to use the sphere volume formula. 4/3 pi r cubed with a radius of a half. 4/3 pi times 1/2 cubed. All right, let's do some simplification here. Just bring down the 4/3 pi, and then cubing 1/2, you just cube the top and you cube the bottom. So 1 cubed is just 1 times 1 times 1. And then 2 cubed is 8, because 2 times 2 is 4, times 2 more is 8. And then let me go ahead and simplify if I can, like this. 4 goes into this 8 exactly 2 times. And now I'm just going to multiply straight across all the tops together and all the bottoms. And understand that the pi, of course, is like pi over 1. So I'd have pi on the top and 6 on the bottom, meters cubed. All right, we're ready. We are ready to find our probability. So probability that our point K is not in the ball would be, we said we're going to subtract them. So it's the all of the volume in between the box and the ball. So that's 1 minus pi over 6 over the volume of the box, which is just 1. Well, a fraction over 1 is just the same thing as the numerator, so I can write this as exactly 1 minus pi over 6. Okay, and maybe I want this as just one complete fraction. If I want that as a complete one fraction, I just rewrite 1 as 6 over 6. And then subtract the top, 6 minus pi over 6. So any of these would be acceptable. 1 minus pi over 6, 6 minus pi, all of that divided by 6. Or maybe we get some sort of decimal approximation in the form of a percentage. Here, let's pull up Desmos here. Oh, look, I've already done it. Okay, pretend you didn't see that. So let's say, for example, that I do this 1 minus pi divided by 6. Okay, and then maybe hit enter, take that answer and multiply it times 100. So we get a percent. You can see it's about 47.6%. Okay, or remember we had another fraction here, which was 6 minus pi, arrow out of that thing, and then divided by 6, and you can see I get the same number, so about 47.6%.